Welcome back everyone. We are doing organic chapter, that is haloalkanes and haloarenes. In the previous lecture, we have discussed about substitution nucleophilic unimolecular and substitution nucleophilic bimolecular reactions. Now, in those reactions, in the mechanism, we have found out the order of reactivity of different haloalkanes towards Sn1 and Sn2. Today we have come to one of the most important part of the chapter, that is optical activity. Before we find out how Sn1 reactions and Sn2 reactions behave or show optical activity, we have to find out we have to learn a few terms, or we have to find out what is optical activity first. Okay, first of all, let me discuss that optical activity deals with light. Okay, optical activity has to take place in the presence of light. Now, you all know that light, normal light, consists of vibrations, consists of radiations which vibrate in all different planes. Okay, so I have made a diagram showing that light vibrating in all different planes. Okay, now if we pass this normal light through a nickel prism, now nickel prism is a special type of prism. Okay, it's a special type of prism which is made up of crystalline calcium carbonate. When you pass normal light, which is vibrating in all the different planes, through a nickel prism, what happens is all the different vibrations are cut off and the light starts vibrating only in one plane. Okay, and this is called plane polarized light. This is called plane polarized light. Then, so we have found out that how we obtain our plane polarized light. Now, what happens when this plane polarized light is allowed to pass through organic compounds? This can be done with the help of an instrument which is known as polarimeter. Now, what is a polarimeter? In the polarimeter, okay, we have first our source of light. This light is allowed to pass through the nickel prism. Okay. After it passes through the nickel prism, you know that it will be converted to the plane polarized light. Okay. Now, this plane polarized light is then allowed to pass through our sample. Okay. This is our setup in which we will add our organic sample. Okay, say we have added glucose here. Okay, after this light passes through the organic sample, what happens is the plane polarized light may show a deflection by some angle. Okay, by some angle which we can observe through another prism which we will call the analyzer. Okay, this is the setup of your polarimeter. Light passing through nickel prism, getting converted into plane polarized light. This plane polarized light is then allowed to pass through an organic sample. The organic sample may or may not rotate the plane of polarized light. If it may or may not rotate the plane of polarized light, which will be observed by us, okay, through the analyzer. Now, the nickel prism will be called the polarizer since it converts it into a plain polarized light. Now, if your organic compound rotates the plane of polarized light, it will be called optically active compound. It will be called an optically active compound. And if it does not rotate the plane of polarized light, it will be called optically inactive compound. That means there is no deflection in the plane of plane of polarized light, or in the plane polarized light. So we have learned two terms, optically active and optically inactive. Okay. Next. So from here we will go to the next section. Now it is not necessary, like I had shown in the diagram. I had shown the deflection on my right hand side. Optically active compound can rotate the plane of polarized light either to the right or to the left. Okay, either to the right or to the left. That means the deflection can be either to the right or to the left. If it is to the right, we will call it dextrorotatory. And if it is to the left, we will call it levorotatory. Okay. Dextrorotatory is also given by plus sign and levorotatory by minus sign. That means if your organic compound, which may be, some examples are optically active compounds of glucose, then we have lactic acid, they rotate the plane of polarized light, and the rotation can be either to the left. If it is to the left, it will be levorotatory, and if it is to the right, it will be dextrorotatory. Done. So we have learned about rotation. Next. Okay, so this plus and minus rotations will be called optical isomers. And the property by virtue of which an organic compound will show rotation in the plane of polarized light is called optical activity. These definitions, okay, of optical activity, optical isomerism, I'll give it in the notes. So they will be optical isomers. Next, what do we need to discuss? What is the condition by virtue of which an organic compound or any compound, okay, or any object will show optical activity? Okay? Suppose you hold your left hand in front of the mirror. You will see the image of your left hand. If you hold your right hand, you will see the image of your left hand. Right? Now, if you try to superimpose your right hand on your left hand, okay, both palms downwards, you will see that you are not able to superimpose these two hands on each other. Done. That means these are non-superimposable. Similarly, our shoes, our gloves, they are non-superimposable on each other. Clear? But if I write the alphabet A, what will be its mirror image? Its mirror image will be the same. Again, if I write the alphabet P, what will be its mirror image? Like this. Now, that means A is superimposable on its mirror image. P is not superimposable. That means if I bring it and try to superimpose it on its mirror image, it is not possible. This shows that there is some criteria for, compounds or objects to show optical activity. Okay, that means this one is optically active, this one is optically inactive. Now, what is that criteria? Let's see. Now, there is one term that is chiral. Okay, now what is the meaning of the word chiral? If your object is not superimposable on its mirror image, we will call it chiral. Not superimposable on mirror image, MIRRO, not superimposable on mirror image is chiral, and a chiral means it can be superimposed. Okay, superimposed. Now, since we are studying organic chemistry, we are dealing with organic compounds. Okay, let's go straight into the criteria or the requirement for an organic compound to be chiral. We know that the valency of carbon is 4. Okay, the valency of carbon is 4. That means it forms 4 bonds. If the 4 bonds which are in tetrahedron, which are at the 4 corners of a tetrahedron, because we know that sp3 hybridized compounds are tetrahedral. If these 4 bonds, or if these 4 groups that are attached to these 4 bonds are different, that means if I write here A, B, C and D, remember this is carbon but this is C, any other group, then what will be its mirror image? C, I will write here D will come here, C will be here and B will be here. If I bring up this molecule and try to superimpose on this, it is clearly understood that this is not superimposable. This is not superimposable. That means this molecule becomes chiral. Okay? This carbon will be called chiral center or chiral carbon or stereo center, or it can also be called stereogenic center. Stereogenic center. Okay? That means the requirement is the carbon should be bonded to 4 different groups. Also, there is one more criteria. What is that? If I pass, so this is my hand, okay? Why is my right hand not superimposable on my left hand? Is because I'm trying to draw my hand, okay, but it is looking very ugly. 1, 2, 3, 4, 5. Okay. Now, if you think about your hand and you bisect your hand into 2 halves. You bisect your hand into 2 halves. Is this half the same as the other half? No, it is not. That means these 2 halves are not equal. When you pass a plane through the center of your hand, these 2 halves are not equal. This plane that you have passed will be called plane of symmetry. Will be called plane of symmetry. Plane of symmetry. Okay? Or it can also be called the sigma plane. It can also be called the sigma, which is given like this, sigma plane. Now, that means if I pass a plane through this molecule, we can clearly see that the groups that are on either side of the plane are not same. That means this molecule is a asymmetric molecule. That means this molecule is asymmetric. The chiral molecules are disymmetric. Okay? The chiral molecules do not have any plane of symmetry and are therefore called dissymmetric. So, chiral molecules are disymmetric. D-I-S-S-Y-M-M-E-T-R-I-C. Chiral molecules are disymmetric. Whereas achiral molecules, for example, if I take A, B, C, B. If I pass a plane through this, you have same groups on either side of the plane of symmetry. So they become symmetric molecules. Okay? And this is a chiral molecule. Done? So chiral molecules disymmetric, achiral molecules symmetric. The carbon which has 4 different groups attached to the same carbon is called chiral carbon, stereo center or stereogenic center. Done? So this is about the optical activity. I'll give you a few more examples. Okay. I'll give you a few more examples for optical activity. Let's see. CH3. Here we have H, H and OH. Clearly this is ethanol. CH3, CH2, OH. Now if we pass the plane of symmetry through the center of this molecule, we can clearly see that these 2 groups are same, right? So this is an achiral molecule. This is an achiral molecule. But the moment I replace this with CH3, this becomes a chiral molecule because these 2 groups become different. Okay. Now, if I draw the mirror image of this molecule, we will get CH3, H will come here, this is OH and this is CH3. If we try to superimpose this molecule on this, we can see that it is not superimposable. Now, the term that you need to remember is non-superimposable mirror images. Non-superimposable mirror images are called enantiomers. MERS, a very important term and a very important definition. What are enantiomers? Non-superimposable mirror images are called enantiomers. Done? Okay, so I'll give you a few molecules for example, which you can draw the mirror image and check for yourself whether they are superimposable or not. Okay, I'll stop here. Okay, let us continue. Now we have discussed about optical activity and we discussed a few terms under optical activity. You learned about chiral carbon, you learned about plane of symmetry, you learned about enantiomers. Okay, now all these optical activity knowledge we need to apply in our substitution nucleophilic mechanism. Now what happens to the optical activity or what happens to the nature of a molecule when it undergoes Sn2 reactions and when it undergoes Sn1 reactions. Okay, we have seen that if a molecule rotates the plane of polarized light to the right, it is called dextrorotatory. It is given by the symbol plus, and if it is to the left, it is levorotatory. It is given by the symbol minus. I have taken an example of a molecule 6, 7, 8. So this is first carbon, second carbon and the 6 carbons. So altogether there are 8 carbons in this molecule and the bromine is in the second carbon. So this is 2-bromo octane. Okay, and the information that I am giving you, it is minus. That means this molecule is already levorotatory. Now this molecule I'm treating it with aqueous potassium hydroxide. That aqueous potassium hydroxide, this will lead to substitution. Now this is my nucleophile. OH minus is the nucleophile, and you have seen that in Sn2 reactions the nucleophile attacks from a rear side, that means from the back side. So this will come and attack from the side which is opposite to the halogen. Now when this attack takes place, the molecule gets inverted just like an inverted umbrella. When you walk out on a rainy day with an umbrella, and you know, if it is not a rainy day but a very windy day with an umbrella, your umbrella goes upside down. Same thing happens here. So OH comes here, CH, and this will remain in its place. So C6H13, and this CH3 comes this side. So CH3. Since this is an inversion of configuration, this is inversion of configuration, the minus 2 bromo-octane becomes plus butan 2-ol. Okay, that means you have changed, you know, due to the backside attack and due to the inversion of configuration, the lever rotatory compound now becomes a dextrorotatory compound. So you must remember that Sn2 reactions, you know, proceed with inversion of configuration. Clear? Next. I've written butan. Sorry, this will be octan 2-ol. So this is octan 2-ol. Okay. Next is Sn1. What happens during Sn1 reactions? Now, we know that Sn1 reactions proceed with the formation of a carbocation. Okay. Let me take an example. 2-bromobutane. So CH3, CH, and we have this one. This is CH2, CH3, and Br. So first carbon, second carbon, third and fourth. So this is 2-bromobutane and 2-bromobutane. Okay, nothing plus, minus, nothing is given to us. We will see why. Now, during Sn1 reactions, the first step is formation of carbocation. That means which is the slow step. So C, and we have CH3, H, and CH2, CH3 plus Br minus. This is my plus sign and this is my minus sign. Now, why I have written it like this is, you all must have studied in class 11 that carbocations are sp2 hybridized, and sp2 hybridization is trigonal planar in shape. So this is very, very important that you must remember that this is trigonal planar in shape. Okay, now this trigonal planar carbocation CH3, this is H, and this is CH2, CH3. This is the positive center. Okay. Now, in the same carbocation, we take the nucleophile OH minus and OH minus. Since this is a planar molecule, the nucleophile can attack from both sides. Okay. If it attacks from this side, this will be called rear attack. And if it attacks from this side, it will be called front attack. Okay, it will be called the front attack. So what will be my configuration here? First we will do this side, rear attack. Okay, so OH, then CH3, rear attack means from back side, this will go this side. So we have CH2, CH3 and H. Then this one is plus butan 2-ol. Okay, and this is attacking from the front side, so this will be CH3, OH, CH2, CH3, and this one is H. That is plus, then this is minus butan 2-ol. Now, interestingly, during Sn1 reactions, both, attack from both sides, the chances is 50-50. So you get an equimolar mixture, that is 50% of plus isomer and 50% of minus isomer. And the mixture of dextrorotatory and levorotatory compound in equimolar proportions is called a racemic mixture. RACEMIC. Racemic mixture. Okay, it is called the racemic mixture which has equal amounts of plus and minus isomer. Racemic mixture is a very, very important term. Now, there is one more term that I want to discuss, that is racemization. Racemization. Now, what is racemization? The process of converting a plus isomer or a minus isomer into a racemic mixture, okay, is called racemization. You want to convert either a plus or a minus into a racemic mixture is called racemization. And one very important note is that that dextrorotatory will rotate to the right, levorotatory will rotate to the left. To which direction will racemic mixture rotate the plane of polarized light? The answer is it will not rotate the plane of polarized light, because both this will cancel out the rotation of each other. Plus and minus in equal proportions will cancel out, and then there will be no rotation at all. Okay, so with this I have finished discussion about optical activity and how Sn1 and Sn2 mechanisms are affected by optical activity. That means they show optical activity. If I have missed anything, I will give it to you in the notes properly. And most importantly, we have exercises and doubt clearing sessions where you can clear all your doubts. Okay, so with this I'll stop my video here. Thank you, class.